Hi guys, so the objective of this video today is to solve the College Board 2005 AP Chemistry free response question number 3, parts A through F in Form B. So the 2005 AP free response question on Form B, number 3, reads, the decomposition of gas X to produce gases Y and Z is represented by the equation above. In a certain experiment, the reaction took place in a 5-liter flask and at 428 Kelvin. Data from this experiment were used to produce the information in the table below, which is plotted in the graphs that follow. Part A reads, how many moles of X were initially in the flask? And that equation should look like this, where you take the 0.00633 moles, which is the number represented at 0 minutes, which is the initial concentration of X, and then multiply that, put it over 1 liter, and then multiply all that by 5 liters, which is given in the flask, right up there. It says in the problem. Right there. And what you should get from that is 3.17 times 10 to the negative 2 moles of X initially in the flask. That's the initial. Focus. There we go. Part B reads, how many molecules of Y were produced in the first 20 minutes of the reaction? So what you gotta do is go back to the data chart and at 20 minutes take the moles of X and set it up with another dimensional analysis equation. So the number I circled in green is the concentration of X at 20 minutes. And you should get something like this for part B. So I took the 0.00427 moles of X at the 20 minutes and multiplied all that by 5 again and got 2.14 times 10 to the negative 2 moles of X remaining. But we're not done yet with that question. What it's asking is for molecules of Y. So what you would do is take the number that you got in part A, which is your 3.17 times 10 to the negative 2, and subtract it from 2.14 times 10 to the negative 2 moles of X remaining at that point, and you would get 1.03 times 10 to the negative 2 moles of X left in the reaction. And with this number, you would use the stoichiometric ratio of the equation up above, which is right there. And you would see that 1 mole of X reacted would produce 2 moles of Y. So you use the stoichiometric ratio of this and Avogadro's number to find the molecules of Y produced in the first 20 minutes of the reaction. Alrighty, so it should look like this. You take the 1.03 times 10 to the negative 2 moles of X, and then the stoichiometric ratio right here, you see that, taken from the equation up above. And that cancels out the moles, then you're left with moles of Y, and then you multiply all that by Avogadro's number to get molecules of Y. And that should give you 1.24 times 10 to the 22nd molecules of Y produced. Ta-da! And that's the answer to part B. Moving on to part C, it asks, what is the order of this reaction with respect to X? And justify your answer. So what we're going to do is look back at our data. So looking at the data and the graphs, I can tell that the order of this reaction with respect to x is first order. And how I can tell is basically by looking at the data, you can see that it pretty much has a constant half-life, but it may be a little off. So another way you can tell if the data is not too obvious is if you take the natural log of the concentration of x, you should get a straight line, which is what the graph on the right shows us. So that's how I know that this reaction is first order with respect to x. And how you would write that would be like this. First order with respect to x. And it's totally okay to abbreviate like that. It's perfectly fine on the AP test. So part D asks to write the right law for this reaction. And it's pretty simple. So basically, the rate law equation anyway is quite simply this. Right there. Rate equals K, K being the constant, and A is the concentration. So this reaction being first order, the rate equation would look like this. So it should basically look like this equation down here. And the number 1 right here represents what order it is. You don't have to put a 1 there if it's a first order reaction. It's kind of just implied that there's a 1 there if there is no exponent anyway, but I'm just showing it for like teaching purposes. So yeah, this would be your answer for part D. And if it was like a second order reaction with respect to x, then the exponent would be 2. So that's just for like the future. Alrighty, on to part E. It states to calculate the specific rate constant for this reaction and to specify the units. Okay, so for this problem, you basically have to use the integrated rate law equation, which looks like this, where the concentration of A, T, is concentration at a random point. T, right here, represents the time, and the concentration at 0 is obviously the concentration at initial. So basically, for the random point, I just picked minutes at 20 and concentration at those 20 minutes. So it's basically just plugging in numbers, and this is what you should get. You can use other points too. I just happen to use the numbers at 20 minutes. And this is what would it look like with all the numbers plugged into the equation. So just do the math. Alright, so basically, you should have all this. The natural log of 0.00427 would be negative 5.456. And then the natural log of the initial concentration would be negative 5.062. And you take this number, add it to the other side, then you would get negative 0.394 and divide that by 20 with the K to get K by itself, and then divide out the negative that the K has, and your final answer for the specific rate constant K for the reaction is 0.0197 minutes to the negative first. Alrighty, last part. Woohoo! Part F asks to calculate the concentration of X in the flask after a total of 150 minutes of the reaction. So what you basically have to do for this is use the integrated rate law equation again, like we did in part E, and just plug in numbers. Alright, so basically what you should have is this. For the K, we can plug in what we found in part E, because that's what we calculated was the rate constant K. And T, for time, it would be 150 minutes, because that's what specifically this question is asking for. And the initial concentration is the same right there as seen in the data. And when you natural log it, it's still negative 5.062 molarity. So it's pretty important to have units, so don't forget that. So like this is minutes negative first, and then over here for time is just 150 minutes, and then the concentration is obviously in molarity. So once you get all your math going, it should end up like this. And your final answer for the concentration of X in the flask after 150 minutes, after 150 minutes should be 3.29 times 10 to the negative 4 molarity. And I'll explain the units more specifically if you're a little bit confused. So basically it's like this. You have your K constant, the 0.0197 to minutes negative 1. You can bring that minutes negative 1 down and make this a fraction. And that's what gets rid of the negative 1, because you've turned it into a fraction. And what you have next is the 150 minutes. So by multiplying, you cross out the minutes and you're left with molarity right there. Another way of looking at it is basically like this. See? You're just left with the molarity. Alright guys, that's basically it. That is the AP Chemistry Free Response Question 2005, Form B, number 3, parts A through F. Yeah, good job. Kinetics is not so bad once you get the hang of it, but just make sure that you pay attention to units and you just concentrate. Alright, good job guys. See you later. Thanks for watching.